built into SPSS. Okay, I'm gonna go up to this function up here, function. So it brings up a box where I can type in t-test, search for the t-test. I'm gonna pop it open. Okay, I'm gonna get some help on it also. I'm gonna open up this help box here. Okay, so first thing that it wants to know is it wants to know what array number 1 is, what the group is, right? And I could put that in here. And now the problem is that it then wants to know what's the group I'm comparing it to. So really, in Excel, I don't really have an easy way to do this, comparing it to a single value. Okay, so we're going to put this function aside, and we're going to open it up again later on when we get into something that's a little bit more complicated. Okay, when we're dealing with more than one group. This is simple enough for us to do by hand. Now, if we really want to not do it by hand, we can do it with SPSS. And I'm going to go here, I'm going to open SPSS. Okay, here's our data now summarized by SPSS. Okay, there's all our data right there. So what we did was let's see if I can't find it here. That's the elapsed time that they reported. Okay, analyze. We were comparing means. We were comparing 45 as a mean to the result of the mean for this sample. Compare means. In this case, it's a one sample t-test, right? It's only one sample involved. We're comparing that to a set number or a known mean for some other population. I'm going to open that up, and sure enough, there's only one variable here, the elapsed time. I'm going to poke it in there, and I'm going to put down here, compare it to the known value or mean 45. Okay, so now I'm going to work with a 95% confidence interval when it does the calculations. That's the only option I got to worry about right now. And then I'm going to say, okay, output table is going to open up. Let's see what we get for the t-value. For the t-value, we get the same thing we got before, 6.5, 19 degrees of freedom. The probability of getting that outcome, if those two 45, if that was really from the same population, if like they were both the same groups, the probability of that happening is less than 0.0001. Okay, very low probability, as we found before. Now, SPSS also calculates a confidence interval for the difference between those values in 45. So if you were to start off assuming that 45 and what the smokers would estimate should be the same, then you would expect the difference to be 0. Now, the confidence interval for the difference turns out to be 9 to 19 or 10 to 19. Okay, so 10 to 19 doesn't contain as difference as 0. So you again have evidence, you're 95% sure that the difference between the smokers and a real measure of 45 seconds is a significant difference. It's more than 95% confident that a difference of 0 is not the case here. Okay, so we got a few ways of looking at this. Significance is the same thing as probability, exactly. Significance two-tailed is the same thing as the p-value or probability two-tailed. Okay, or area of the distribution outside of that, or probability that you would get that outcome if there's no difference between the two groups. Okay, so now we're going to really put this to work, because most of this kind of stuff that we've done so far is not something that you do very much. I'm going to move this away. I'm going to open up another version of this file that I created. I don't want to exit this. I'll just go do it this way. Open data. And let me see if I can't find it. 1A. Let's see. Did I make 1A? I'm going to have to import it. Excel. 1A. I'm going to open it. I'm importing this file because I have it as an Excel file. Go ahead and import it. Okay. And now let's say that I did this, but instead of assuming that the smokers, then non-smokers would get it in 45, would guess 45 seconds as their mean for a real 45-second period passing by. Let's say I actually measured non-smokers. Well, there's a few things that could go on here. I'm going to compare this group to this group. I don't know the real mean of this group for the whole population of smokers. I don't know the real mean of this group for the whole population of smokers. In fact, I don't know the standard deviation for this group for the entire population, right? And I don't know the standard deviation for this group for the entire population. I might have sample sizes. I have 20 here and I have 22 people here. I might have sample sizes the same for these two groups or different for these two groups. And I might find that the standard deviation for this group is very different from the standard deviation for this group. In other words, this group might have had values 20 to 120, and this group might have had values 40 to 60, clustered very much more tightly, which would influence how certain I was of what the real true mean of this population and what the real true mean of this population is. Nonetheless, I want to calculate a mean for this group, because we want to estimate the true population mean for smokers and non-smokers, and I want to compare the two of them. I want to know how many standard deviations apart that these two groups are. SPSS is going to allow me to do this. I'm going to go into Analyze, Compare Means, okay, and now I'm going to go into, not going to use one sample t-test because now we're dealing with two samples. And I'm going to go into independent samples t-tests, okay, because later on we're going to learn something about paired samples t-tests. They're independent samples t-tests because we independently sampled smokers and non-smokers. In other words, person number one has nothing to do, who's a smoker, smoker number one has nothing to do with non-smoker number two. They were completely selected from their two groups independent of one another. It's not like these two guys are brothers, these two guys are cousins, and so on and so forth. They're independent samples. Okay, so compare means, independent samples t-test, not one sample, not paired samples, but independent. Okay, so now I'm going to put in here, well, I got a little bit of a problem here. The way SPSS groups data, okay, I really need to separate these two groups differently from this, right? I'm going to go back into Excel and I'm going to take care of that. Okay, let's move this away for now. Okay, and I just want to show you that so that, like, you see there can be a little bit of difficulty with just directly importing data into Excel, but we're going to fix that in a moment. Okay, I'm going to go in here and I'm going to open, let's see if I got it open. Okay, let me get my documents. Okay, 1A. Here's my two groups of numbers. I'm going to zoom in a bit more. Okay, there's my two groups of numbers. And I'm going to say, okay, I'm going to do the t-test that we just described that we couldn't use when we're only dealing with one sample. It's going to be equal to, well, let's use the function because it'll help us as we go through it. T-test. Okay, there we are, ready to accept our t-test. I'm going to open up the help function again because we're going to need it in a moment. Okay, array number one, that's easy. That's just group number one. Okay, and it's those guys there. Okay, array number two is just this other group, non-smokers. Okay, and the number of tails is going to be, it's two-tail, and we're going to use a two-tail test because we don't know if smokers or non-smokers are going to be higher numbers or lower numbers. We're going to assume that we don't. Also, it's a more rigorous test, so it's a safer test for us. Okay, and then it's going to ask me for the type of variable, and then you can get into this help menu, and you can it'll describe these selections here a little bit better for you, but it summarizes it here. T-test paired is equal to 1. They're not paired, they're independent samples. Two samples with equal variances, a homeoscedastic is equal to 2, and two samples with unequal variances is equal to 3. I'm going to show you a little secret here. If I type in, we know it's not going to be 1, it's going to be either 2 or 3, depending on what you might, for starters, might just assume, well, there's no reason for me to think that the variance is going to be the mean value might be different, but I don't have a whole lot of reason to think that the variance is different. But so let's put down a number 2 there to start off with. Excel automatically calculates the result. You see it down there? It's kind of light, it's kind of small. It's 0.01. There's 1% chance. In other words, the p-value, it doesn't, you don't actually see t here. It actually calculates the p-value for you. The probability of these two groups being from the same population is less than 1%. Okay, so now let me see what would happen if I put a 3 in there and assumed unequal variances. Okay, well, it's 0.013, a little less probable, right? So in other words, assuming equal variances, let's see, 0.01334, 0.01335. It's really pretty much about the same, isn't it, for this particular distribution? So I'm going to assume that they're equal variances for the moment. I'm going to hit enter, and that's my probability. That's my p-value. Okay, going backwards now. What we're trying to prove is that there's a difference for smokers and non-smokers in the way that they estimate the passage of time. Okay, so what would have been, going backwards, what would have been our null hypothesis? H null. Okay, our null hypothesis, anybody want to propose a null hypothesis? Mean time smokers equals the mean time for non-smokers. Okay, they get any takers there? Oh yeah, or absolutely right. Oh, excuse me. Null hypothesis mu equals 45 would have been, and mu does not equal 45, would have been a good null hypothesis for the previous problem where we were comparing one group to the number 45. That would have been perfect for our null and alternative hypothesis there. In this case, we're actually comparing two groups to each other. So the mean for smokers equal the mean for non-smokers. And similarly to the way you reasoned that the mean equals 45, we would say that our alternative hypothesis, okay, is not equal to the mean time estimated by non-smokers. Okay, so given that we have a p-value of 0.01 is 0.01, in other words, there's 1% chance that these two came from the same population, would we accept or reject our null hypothesis? Okay, 0.01 is our p-value or probability. It's less than 0.05, our normal alpha. We reject the null hypothesis. We reject the null hypothesis. We accept the alternative hypothesis that the true mean population estimated 45 seconds time is different for smokers and for non-smokers. Exactly right. Just for the hell of it, we can use t-dist to actually go back a step, comma. Now we need to know the degrees of freedom. If these are equal size samples, the degrees of freedom would have been n1 plus n2. And in fact, many times I'm going to just use that for argument's sake. n1 plus n2 is equal to minus 2, which is 20 and 22 would be 40. Okay, so I'm going to use a sample size of 40, comma 1, comma 2, two-sided test. So, oops, I made a mistake there. Equals t dist parentheses. Okay, no, it's like, see, I'm doing that right. A t inverse I need. T dist would have taken the t value and given me a p value. I think I need t inverse. Okay, which gives me the probability, common degrees of freedom. I'm going to call it 40. Okay, so the t value was actually 2.6 for this particular study, okay, to get that p-value of 1%. Okay, so now let's notice that's a big sample size because we have twice as many. We assumed it was equal. One of the things that's going to happen is that when you have samples like this and you assume equal variances, you can, instead of just assuming that since you have reason to believe that the variance of this group and the variance of this group is the same, even though you can only use these numbers to